Hey guys, welcome back to another JavaScript tutorial, and in this tutorial I'm going to be talking about memoization, how to use it and why it's really useful. So memoization is basically a technique which allows you to store results of a function call in a cache and then just display those results once the function's been called again. So if the function is really if it takes a long time to run, then you can literally just go to the cache and it will just give you the answer straight away, especially so it leads to less redundant operations. So I've actually got an example for you guys. Let me just find where did I leave it? Memoization, here we go. So yeah, I've got an example for you guys. Let's say we have a function, let's just say add two numbers. We take in two numbers and we just return this, right? Now obviously this function is really cheap, as you'd say, so it's not going to cost anything, or it's going to be really fast to add pretty much any number. So even if I type in some huge numbers, this function will add them no problem, really fast. But let's just say that this pretend this function call takes a long time. Let's just pretend this is a really expensive function. So now we have this really expensive function, and we just want to actually might as well just let's just say expensive function just to illustrate the point a bit more. So we have an expensive function here. Now what we do is we want to minimize the amount of times that this code actually runs, because every time this code inside of it runs is going to take a really long time, right? Because it's an expensive function. So what we can do is we can implement a cache. So we can say expensive function cache, and this is just a dictionary. And what it's going to do is we're basically going to encode the information within these two parameters. So say encoded information, and that can just be as simple as doing something like putting them both into an array and then stringing it like so. So now we've got this in a string, and then what we can do is we can actually just add the result of this to the cache. So first of all, we're going to check if it's in the cache. So if expensive function cache encoded information, if this has it in the cache, so if it's not equal to undefined, so if it was in there, then this would not be equal to undefined. Then we'll just return this like so, and if it's not, we'll have to still do the calculation. Obviously there's no choice, but instead of just simply returning it, we can do something like this is the answer, and we can just cache this before it goes, so that next time when we take the same inputs, it'll just give out the cache version rather than doing out the entire computation. So let's just cache this, not answer, if we want to do the encoded information, and there we go. So now we've implemented memoization. It's actually really simple. All you have to do is implement a cache for your functions. So now if we do the same call, actually I'll just show you, we can just use it during console logs because it might not be immediately obvious. So we'll say performing calculation, and over here we'll say using cache. Okay, so now you can see okay, yeah, so the first time this runs, since the cache is reset every reset, so here's the first time. Now if we call it again, we'll see it's using the cache. So first time it had to actually perform the calculation, and second time it actually started using the cache like so. Now I'll just show you guys another example. So obviously if we put in a different number, let's just say we had 7, then it's still going to have to perform the calculation because it's going to be a different answer otherwise. But then again, once it's done it for the first time, it can just use the cache again, and then every other time after that it can just keep using the cache like so. So there we go, that was an example, and now I'll show you a more concrete example, I guess, using the Fibonacci sequence, because this was alright, but we couldn't really see the results firsthand because adding two numbers is already really fast. So let's do one more example. Let's have the Fibonacci sequence. So we can have Fibonacci, and it just takes in the number of like the nth Fibonacci number, like so. And if you know how Fibonacci sequences work, this is basically just going to return the Fibonacci of n minus 2 plus Fibonacci of n minus 1. Because if you look at Fibonacci, they go 1, 1, 2, 3, 5, 8, 13, 21, 34, like so, on and on. So you can see if we want to get the fourth Fibonacci number, which would be this one over here, 3, then that's just 1 plus 2, and 2 is just 1 plus 1, like so. And this also comes down to if we have n, so if n, actually we're going to be 1 indexing, so not 0 indexing, so this first one is index 1, not index 0. So if 1 is less than or equal to, actually our 0 indexed, yeah, that'll probably be better. So if this is index 1 or index 0, so if it's less than or equal to index 1, then we're simply going to return 1 because there's nothing before this, you know. So now we actually have our Fibonacci sequence all set up. It's actually that simple. We just have a recursive algorithm, and this is actually the power of recursion. It can be really simple, but let's show you. So if we want to get the fourth Fibonacci number, we get 0, 1, 2, 3, 4. So remember it's 0 index, and yeah, it works fine. So if we go up to the 9th, actually I'm going to do the 8th just because I have that. Yeah, so we have 34, which is this, so on. But you might notice this is a recursive algorithm, and I've actually set up this example before and seen it somewhere. But if you look at this nice recursion tree, you'll see to calculate fib of 4, you have to keep going backwards, but every time you're going to be doing redundant calculations because it's going to call what fib of 3 is, but that's going to call what fib of 2 is, but you're also directly calling what fib of 2 is anyway. So, you know, you can see why this is doing a lot of redundant calculations for no reason. So this is a kind of program which would really benefit from memoization. And just to give you an example, if we try and calculate fib of 1000, it's going to take quite a while because it has to do so many redundant calculations. See how it's taken a very long time, loading bar. And yeah, so I'm going to show you guys how we can accomplish this way faster using memoization. Let me just cancel that, don't want it to crash. Okay, so now let's implement a memoization cache. Const memoization cache. Again, it's just a dictionary, and now all we're going to do is we're just going to say, so we don't even need to encode the information because it's already in number form, so we don't even need to do that. Now all we're going to do at the start is if memoization cache n is not equal to undefined, then we will return it like so. Otherwise we're just going to do this, but remember we have to store the results before we return it so we can cache it later on. So now let's cache it, result, and return result, of course. Oh, just realized did not do that properly. Yeah, so there we go. Now we cached it like so. So this should make our code a lot faster because it's not having to complete these redundant calculations again. Like if it's already calculated fib of 2, then there's no need for it to calculate it again over here. So this should definitely make it faster, especially for larger numbers. And let's just test it. And okay. And not sure why it's not doing anything. Okay. Oh. Let's just see what's going on here. let's just test, because I'm not sure why it's not printing anything. Might have to restart. Okay, let me just restart this. Maybe it broke after I forced the stop restart. Okay, there we go. So see how fastly it was able to calculate that this huge number, e to the 208. That's a number with 208 zeros, and it just calculated that in a few seconds. I'll just do something smaller, but you can see the idea. Like, it's able to complete them so much faster now because we weren't having to do it like this. Just for comparison, I'll show you Fibonacci with cache, and then we'll do without cache, just to show you guys the comparative speed. So in this one, all we're going to do is we're just going to take this code. Okay, so we can do Fibonacci with cache like so, and see how fast that is. What is going on here? Oh, yeah. Okay, gotta replace all these function calls. So Fibonacci with cache was incredibly fast, and now let's try the same thing, Fibonacci without cache, and oh, look how long it takes. Still loading, and there's a good chance that this won't be able to load. But yeah, hopefully you guys can see the usefulness of memoization. You can able to turn these super slow function calls into really speedy ones just using caching of functions. So before you actually perform a calculation, check if you have the result already stored in cache, and if you do, you can just return that. Thanks for watching, and I'll see you guys in a future tutorial. Bye.